Good morning, everyone. In this video, I will explain the resource-constrained project scheduling problem, commonly referred to as RCPSP. By the end of this session, you will understand the core constraints of RCPSP, why it is computationally difficult, and most importantly, you will see exactly how resource limitations impact project duration through a detailed numerical example. Let us begin by defining the fundamental problem. Traditional project scheduling focuses almost exclusively on precedence. It asks what must happen before what. For instance, you cannot paint a wall until the drywall is installed. However, in the real world, logical order is only half the battle. Consider a construction site where two different tasks require the same specialized crew at the exact same time. Logically, these tasks might be independent, neither depends on the other. But physically, they cannot occur simultaneously because there is only one crew available. This discrepancy between theoretical unlimited capacity and practical physical limitation is precisely what necessitates the RCPSP. Without accounting for resources, a schedule is merely a wish list, not an executable plan. So, how do we formally define RCPSP? It is a mathematical modeling framework designed to determine start and finish times for all project activities while minimizing total project duration. Crucially, this minimization must adhere to two simultaneous rules. First, the logical order rule. Predecessor tasks must finish before successors begin. Second, the resource limit rule. The total resource consumption at any given moment cannot exceed the maximum available capacity. Unlike budget, which is consumed and gone, RCPSP primarily deals with renewable resources. These are resources like labor or equipment that replenish periodically. Once a worker finishes a task, they become available again for the next one. The challenge lies in satisfying both rules simultaneously while finding the shortest possible timeline. Before we move to example, let us review the model's building blocks. An RCPSP model consists of activities, fixed durations, predecessors, and resource profiles. A critical assumption in standard RCPSP is non-preemption. This means that once an activity starts, it must run continuously to completion without interruption. You cannot pause a concrete pour halfway through to let another task use the mixer and then resume later. This constraint significantly reduces scheduling flexibility. Our primary objective remains minimizing the make span, which is the total elapsed time from project start to absolute completion. Remember, introducing resource limits inherently delays tasks compared to the unconstrained critical path. Our goal is to find the optimal sequence that respects these limits while keeping the make span as short as possible. Why is this problem so challenging? RCPSP is formally classified as NP-hard. This means there is no known algorithm that can solve large-scale instances optimally in polynomial time. As we add more tasks, the number of potential schedules grows exponentially. For small projects, exact methods like branch and bound can guarantee optimality. However, for real-world applications, we typically rely on heuristics and meta-heuristics that deliver high-quality, feasible solutions quickly, even if they cannot mathematically prove optimality. Despite this difficulty, RCPSP is indispensable across industries. Construction firms use it for crane allocation, manufacturers for job shop sequencing, software teams for programmer assignment, and hospitals for operating room scheduling. Mastering these foundational concepts is essential for advanced domains, including human-centric scheduling. Let's look at a numerical example. Here we have a set of jobs, their durations, and specific requirements for labor, machines, and materials, alongside logical dependencies. Now, let us walk through a concrete numerical example to see how RCPSP scheduling works in practice. In this demonstration, we will evaluate the specific job sequence, J1, followed by J3, J2, J4, J5, and finally J6. Before we begin assigning jobs, please direct your attention to the three resource profiles displayed on screen. We are tracking three distinct renewable resources simultaneously: labor, machine, and material. On each chart, the y-axis indicates the quantity of that specific resource available or consumed at any given time. A fundamental rule in RCPSP is that an activity's execution must be synchronized across all required resources. You cannot consume labor for 4 days, but machines for only 2. The start time, finish time, and duration must be identical across every resource profile for a single job. With that established, let us assign the first job in our sequence, which is J1. Since J1 has no predecessors, it is eligible to start immediately at time 0. According to its resource profile, J1 requires 3 units of labor, 2 units of machine capacity, and 1 unit of material. Its fixed duration is 4 days. Therefore, on all 3 schedules, we block out resources from day 1 through day 4. On the labor chart, you see a bar consuming 3 units for this entire period. On the machine chart, a corresponding bar consumes 2 units for the exact same time frame. And on the material chart, 1 unit is reserved identically from day 1 to day 4. This synchronized allocation ensures that J1 has all necessary resources available continuously throughout its execution, satisfying both the non-preemption assumption and the multi-resource constraint. This forms the foundation upon which all subsequent jobs in the sequence will be scheduled. Moving forward in our sequence, we now assign the next job, which is J3. Recall that in RCPSP, both precedence and resource constraints must be satisfied before any job can begin. For J3, the precedence relationship specifies that J1 must be fully completed first. Since J1 finished at the end of day 4, the earliest possible start time for J3 is time 4. Now let us examine J3's resource requirements. This job requires 1 unit of labor, 1 unit of machine capacity, and 3 units of material. Its fixed duration is 2 days. Before confirming the schedule, we must verify that these resources are available from time 4 to time 6 without exceeding capacity limits. Assuming no other jobs are currently occupying these resources during this window, J3 can indeed proceed as planned. Therefore, on all 3 resource profiles, labor, machine, and material, we now allocate J3 starting at time 4 and finishing at time 6. On the labor chart, a bar consuming 1 unit appears from day 5 through day 6. On the machine chart, 1 unit is similarly reserved for the same period. And on the material chart, 3 units are blocked out identically across those 2 days. Note again the synchronization. Despite differing resource quantities, the start time, finish time, and duration remain perfectly aligned across all 3 schedules. This ensures J3 executes continuously without interruption, satisfying both its precedence dependency on J1 and the multi-resource feasibility requirement. With J3 now placed, we continue building the schedule according to our predefined sequence. Now, let us proceed to the next job in our sequence, which is J2. According to the precedence constraints, J2 depends on J1, meaning it cannot begin until J1 is fully completed. Since J1 finished at the end of day 4, the earliest theoretical start time for J2 would be time 5. However, this is where resource constraints come into play and override simple precedence logic. Let us examine J2's resource requirements. It needs 2 units of labor, 2 units of machine capacity, and 2 units of material. Now, check the current resource availability at time 5. While labor and machine capacity are indeed sufficient, each has at least 2 units free, the material profile tells a different story. At time 5, only 1 unit of material is available because J3 is still consuming 3 units through day 6. Since J2 requires 2 units of material, but only 1 is available, the schedule is infeasible if we attempt to start J2 immediately. This illustrates a critical principle in RCPSP. Satisfying precedence alone is not enough. All required resources must be simultaneously available. Therefore, J2 cannot begin at time 5. It must wait until the material constraint is resolved. Looking ahead at the material profile, we see that J3 finishes at the end of day 6, releasing its 3 units of material. By time 7, all 3 resources, labor, machine, and material, are sufficiently available to support J2's requirements. Consequently, J2 is scheduled to start at day 7, not day 5, despite being precedence-ready 2 days earlier. This delay exemplifies how resource limitations directly extend project makespan beyond what logical dependencies alone would dictate. This slide presents the complete project schedule generated from our specified sequence: J1, J3, J2, J4, J5, and J6. Looking at the Gantt chart across all three resource profiles, we can see that the total project duration, or make span, is 17 days. This represents the elapsed time from the start of J1 at day 0 to the completion of the final job, J6, at day 17. I would like to draw your attention specifically to job J5. Notice that J5 is scheduled to execute in parallel with both J2 and J4. You might wonder why this overlap is permitted. The answer lies in satisfying both constraint types simultaneously. First, regarding precedence, J5 depends solely on the completion of J3. Since J3 finished well before this point, the logical dependency is fully satisfied. Second, regarding resources, during this overlapping window, the combined resource consumption of J2, J4, and J5 does not exceed the available capacity for labor, machines, or materials. Because both constraints are met, there is no reason to delay J5 further. This highlights a fundamental scheduling principle we apply throughout RCPSP, the as soon as possible rule. When assigning jobs according to a given sequence, we always attempt to place each job at the earliest feasible start time that satisfies all precedence and resource constraints. We do not intentionally create gaps or delays unless forced by infeasibility. In this case, J5's ability to run concurrently with J2 and J4 demonstrates effective resource packing, which is essential for minimizing makespan. Had resources been insufficient during this window, J5 would have been pushed later, extending the total project duration. Thus, the final makespan of 17 days reflects the optimal compression achievable under this specific job sequence and the governing constraints.
This slide presents the project schedule generated under a modified job sequence, J1, J2, J4, J3, J5, and J6. As you can see from the Gantt charts across all three resource profiles, this reordering has significantly altered the job allocation pattern compared to our previous sequence. Most critically, the total project duration, the makespan, has increased to 23 days. Recall that in our earlier sequence, J1, J3, J2, J4, J5, J6, the makespan was only 17 days. This new sequence is therefore 6 days longer, representing a 35% increase in project duration, despite involving the exact same set of jobs with identical durations and resource requirements. The difference arises entirely from how jobs are ordered and consequently packed within the available resource envelopes. In this less efficient sequence, resource fragmentation and forced idle periods accumulate, delaying downstream activities and extending the overall timeline. This comparison illustrates the central challenge of RCPSP. The optimal solution depends not just on individual job characteristics, but on finding the precise sequencing that maximizes resource utilization while respecting all constraints. Our ultimate goal in RCPSP optimization is to identify the job sequence that yields the minimum possible makespan. However, because the number of potential sequences grows factorially with the number of jobs, exhaustively evaluating every possibility is computationally infeasible for all but the smallest instances. This combinatorial explosion is precisely why RCPSP is NP-hard, and why developing effective meta-heuristic approaches, as we will explore later in this course, is essential for solving real-world scheduling problems efficiently.
To summarize, RCPSP extends basic scheduling by integrating strict resource limits alongside logical precedence. A valid schedule must satisfy both constraints at every point in time. Our numerical example proved that makespan is highly sensitive to job sequencing under resource constraints. Different sequences lead to different levels of resource utilization and parallelism, directly impacting project duration. Because RCPSP is NP-hard, finding the best sequence for large projects requires sophisticated heuristic approaches rather than simple rules. Understanding these mechanics is foundational. As we progress toward human-centric scheduling, remember that human resources introduce additional layers of complexity, fatigue, skills, well-being, that make the sequencing decisions we explored today even more critical and nuanced. Thank you for your attention.